The old and glorious days. People have this notion that these in many cases, so it's a good space. So the question is, how do you know here? Thinking things that are outside of those limited subsets of mass. First, how do you protection of place things built into the original completely, literally smooth rivets. Yeah. Very I think that's interesting. The SHIELD program is creating a very sophisticated device. One of the challenges with having very sophisticated devices technically sophisticated tax. Where is that device allowed to be in?
Anyway, so I said that the DevSecOps launched this year.
Begin to realize that there's
a lot of the same principles
measure there's security.
It seems to be capable of really miniaturization.
Yes. Wow.
Yeah.
Let me get some water.
Oh, yeah. You know where did you see the water dispenser?
That's why I was picking my way through here.
Yeah, so we've also been with security full-time
Okay.
Yeah.
So, no, it's not. Yeah. My role in API is as a subcontractor to other companies. Okay. And their interest from us was practices of what I worked in power system operations for most of the 40 years. So they wanted to know how to integrate devices into processes. I said,
I think we're ready to rock and roll.
oh, yeah.
Are you good?
Yeah. Would you care for a business card?
Oh, yeah. Only if you want it.
Wasted. Well, thank you so much. Thank you. Yes. So that's a gadget. Yep. Wow. Interesting.
Sure, you let me know when you're ready to go.
Oh, yeah.
classmate. So we have a project in a course. I just call it IT because the name is so long. So we do like a consulting project for 7 companies, and one is your company. Yeah.
Good.
Actually, the professor, they just assign us one staff from the area, and one is your company. So
How are we doing?
well, I will try to understand. I think that like last Friday we understood what is the technology about.
Yeah, and just a couple
because,
minutes
like,
to start.
So I hope it's going to be more. I think
Yes, I thought Joshua.
Yeah, of course. Yeah, sure.
DevOps.
Yeah, thank you. Nice to meet you.
Yep.
Yeah.
Good. All right. Okay, folks, we're going to kick off our April meeting. So if you could all grab some food if you haven't done so already, take a seat. I'm going to start off with our wonderful host. First of all, big hand for WPI for helping us once again. Amazing facility. And as some states, it gets prettier every month. I'm going to pass the mic over to Mike to talk to you just a little bit about WPI and their programs.
Well, thanks, Paul. And I see familiar faces. Who has not been to this facility before? So a few people. So let me just tell you, Worcester Polytechnic Institute is a technical polytechnic university out in Worcester, Mass, about an hour west of here. And we're finding more and more of our students and companies interested in having us teach for them are here in Boston. And so we thought we'd rent this facility. We've rented this for about a year. We're very pleased to host things like this meetup. This is the 4th one, I think, Paul, that we've hosted.
That's right.
And the weather gets better and better because it was pretty bad before.
Those two things are unrelated.
And I guess I'll just mention that one of the newer things at WPI is we have had an online graduate program, a certificate program in cybersecurity now for a few years. Now it's kind of scaled up. If a student wanted to, they could earn a master's MS from us in computer science with a concentration in cybersecurity entirely online. So that's the new news from WPI. Thank you, Paul.
And Joshua? Jason. All right. Sorry. I just met him 5 minutes ago.
I gave you that.
You did. Damn you, Mike.
Hi, everyone. I'm Jason Wolanick. I'm here from the Boston DevOps Meetup. We host DevOps Days in Boston. Our next conference is going to be September 23rd to the 24th. If anyone is interested, please let me know. Tickets are $250 a piece. I have a 20% discount code for people who register early. So if you guys are interested, come and see me. And hopefully I'll see you guys there. If you'd also like to check out the Meetup, we're also on Meetup app. So just look up DevOps Boston. Swing on by. Feel free to come to the event. Thank you. Thanks.
Okay, so I'm really excited about our speaker this month, Ophir Gaathon from Dust Identity. We've actually had a couple meetings, and in fact, if you're a Security Ledger podcast subscriber, this week's podcast, which is coming out today, is an interview I did with Ophir as well, recorded interview. Probably might be a little bit repetitive to you because I think some of the stuff you're going to cover today, but I think we probably cover some ground that you're not going to. But really fascinating company, kind of on the cutting edge. So in this meetup, we've talked a fair amount about IoT risk in various forms and about supply chain risk in particular. And
this is an issue that more and more is becoming really integral to organizations, sophisticated organizations, whether those are companies like Apple and Amazon that run huge cloud-based server infrastructure, whether it is, a financial services company that has surveillance, security cameras, and other kind of connected infrastructure, building automation systems, and so on. Supply chain third-party risk is becoming huge, and supply chain is really a big kind of component to that, right? Which is, if you're Amazon and you're buying server hardware to run your huge cloud-based AWS infrastructure, how can you make sure that the components that are in the hardware that you're buying are on the up and up, that there isn't a malicious component, a backdoor component on that rather large and complex server motherboard. We saw this with recently in October, Bloomberg came out with a big story, right, about Supermicro. It was very controversial. It was very unclear whether they got the story right or they got it wrong. But regardless of whether Bloomberg got the story right, I think the problem that they were highlighting, which is this risk, the supply chain risk of Trojan components, counterfeit components, tampered with components, not just ones that are malicious, but maybe ones that are just of inferior quality, right, is a real concern, and companies don't have a great way to control it. I mean, if you're Apple or Amazon or Raytheon or Lockheed, you probably have pockets that are deep enough to give you some insight into that. But if you're just a regular company, a downstream consumer of some of this technology, it's not easy to do. And that's kind of one of the problems, and there are many problems that dust identities technology addresses in what I think is really just at like the 100,000-foot level, really cool way. And then when you get down kind of into the weeds, a really interesting way that I think is just a great kind of security and identity story that has applications in Internet of Things, as well as frankly a lot of other use cases. So I'm really happy to welcome Ophir here, and I'm going to turn the mic over to him, and I think you're going to be really interested in what he has to say. Welcome.
Thanks, Phil. I appreciate it. Hi, everyone. Thanks for having me. This is a great opportunity to tell you a little bit about what we're doing, but primarily about why we're doing things. I will try to make it as less of a sales pitch as possible, even though on my daily routine, this is what I typically do. So forgive me if I go on that side. But just to light things up, I thought maybe we can start with just showing you a demo of how our solution works. And I need a volunteer for that, if possible. Omar? Anybody that plays cards? All right. Do you play cards?
Casually.
Okay. So this is the first time that we meet, right?
Yeah.
So if you can take the deck out of the box, I'll take the box. Maybe you can make sure that all the cards are real and they're different and there's nothing fake.
I don't have the equipment to do that.
Well, just visual inspection, which is typically what actually people in the supply chains are using. It looks the same, right? You can show it to the audience. They're all different. Maybe you can shuffle them. And yeah, you can count them. Yeah. So what we've done here is just to speed things up. Every one of those diamonds have a unique identity in our system. And the way that we created that unique identity is actually putting diamond dust on the backside of those cards, such that we can authenticate them and demonstrate to other people how our technology works without diving into the specifics of any other object that we typically have to deal with. We almost never have to authenticate playing cards. Just put it out there. So you shuffled it well?
Yep.
You're comfortable with that? Okay, great. So if you don't mind, just let's take one card. Don't show it to anyone. So select one. You can cut the deck. Then take one card. Great. And just put it here. And what I'll do is that I'll scan it. So you can just inspect and make sure that I'm not doing anything not right. So just to make sure, what you see here is this is our cloud app, and what I have to do before I can authenticate anything is actually I have to bring in my credentials.
Our solution is designed like a credit card. So there's diamonds on every one of those cards. That's a credit card. Then we have the scanning device, which is the point of sale. And then we have the authentication of the clearinghouse that allows us to process those credit cards, such that every time we're actually creating a transaction, we're putting in the credentials of the user, the operator, in order to start building that provenance, building that chain of custody. The first thing is that I'm logging in myself. And now I'm going to take the scanner. And you can see that there is some schmutz. That's a technical term, by the way. There's some schmutz on the back of the card. And now it tells us that it's the ace of spades. Do you mind actually turning it over? Making sure that it's. It is. It is. Okay, great. So we have ace of spades. Awesome. So what we've done here. Thank you.
You found the perfect cheat for poker.
What's that?
The perfect cheat for poker.
Yes.
That's for
Yes.
Vegas.
We're not allowed to do this in Vegas. That's what we're told. So what do we have here? Is by the way, thank you very much. Please thank Omar. I did not thank. Fantastic for. You picked the best card. So what do we have here? We basically created an authentication transaction. That authentication transaction allows us to pull data from different places across the supply chain. So we don't make the assumption that everybody, we're not like any social network that makes the assumption that the data, your data is ours. We make the assumption that your data has to stay with you. And what we do is that we pull that data whenever it's necessary to authenticate one of your cards or one of your objects. So there's metadata that is associated with the object, and then there's the transaction ledger, which basically allows us to identify the location, and I believe that we're here. So it actually uses the computer as a way to have the location services added to every transaction that is associated with this object. And this is essentially what we're doing time and again on just very different objects. Does that make sense? Right. So with that, that was sort of like the demo. And the motivation for that has to do with boards that are, do you want me to stay on the mic? Well, I have to. Okay. Can everybody hear me?
It'd be good if you spoke up a little bit.
Okay.
Thank you.
I'll try to. So anybody seen one of those green things in the past, right? These are circuit boards. And you look like the person that might be able to tell us what the circuit board is.
It's the National Instruments USB interface or something.
Exactly. And what happened was that about 3 years ago, we're a spin-off from MIT. We started to work with DARPA on a contract that has to do with developing quantum sensors for completely different applications in the neuroscience. And we started buying those cards to run our instruments. And fast forward, DARPA put us in about 2.5 years ago in front of supply chain security concerns, and we developed DUST, the solution that I mentioned before. And then we started to look at how our solution can fit on different objects. And then we found out that actually we have one of the reasons why we are creating this. And here we have 2 boards that have the same serial number that we bought as a lot. And you're welcome to see. So either one of them is fake or both of them are fake. And this is basically, and you're welcome to actually pass it around. This is the biggest problem here, is that when you're holding something in your hand, can you trust it? Do you have enough information about this object? Can you tell the difference between a real object and a not so real object? Is there a way for us to know if somebody was trying to tamper with this circuit board, replace components, change the firmware, change the design, insert a tampered device, or insert a non-compliant part to a very expensive asset? So with that, I'll just move here. So that ability to trust has to do with our ability to recognize the object, to recognize subsystems in that object. And we came to the notion, and this is very obvious to, I think, everybody in this room, that you cannot trust something without having an identity, without being able to call a name.
can't really associate any information with an object. And if you can't really measure something, how can you manage the risk that is associated with that information or lack of information? So the notion of trust actually has to do with the ability to associate data with something in order to be able to start building measures of trust, or to be able to reduce the risk that is associated with any object. The way that the Department of Defense is calling it, this is a pretty lengthy, but the idea is to have something that is free of exploitable vulnerabilities. And that's sort of like the definition, the DoD definition for what is trust. So maybe to give you a little bit about our history and how we started, and as I mentioned before, it was about 2.5 years ago that we started looking at supply chain security concerns in the context of the Department of Defense. Paul made the point earlier that there could be very wealthy, very large organizations that have the security in mind, like Apple, like Lockheed. But even in those places, even in supply chains that we consider the most secure ones, we actually see that there are vulnerabilities, there are concerns with being able to authenticate things. And it's not necessarily just strictly on hardware. It's anything that goes into very expensive assets. So it could be the batteries, it could be the rivets or the screws, or any kind of mechanical systems that are being inserted into expensive assets. When I say expensive assets, I mean defense platforms, so it could be fighter planes, submarines, weapon systems, it could be data centers, it could be critical infrastructure, it could be manufacturing facilities, it could be hospital equipment. In all those places, the parts that are going into those expensive assets, it's actually much more difficult for us to be able to authenticate and identify them than you would think. Many people make the assumption that we're able to use tools like UDIs, unique device identifiers, or functional testing. The automotive industry has this notion that if I can verify the function of an object, it operates the same way that it should be, and therefore I can trust it. The challenge is that actually rolling out those solutions is actually quite complicated. So about a year ago, for us, things started to be a little bit more out in the open. So this story about the Supermicro story, the concern about insertion of specific components on circuit boards, without going into the details of that story, this is one of the use cases that we developed the solution for. It's the ability to recognize all of those components that are on this circuit board and make sure that they were sourced from the right place, that they haven't been tampered with, that they're true to the bill of material of the object. And when you're trying to think of a solution that is trying to address this, the biggest challenge is, well, there are multiple challenges, but one of them is that if you look at the circuit boards, those components are tiny. They're very, very small, and they're very inexpensive in many cases. So you need to develop a solution that can fit on very small things, and it has to be extraordinarily frictionless from an economic standpoint, and still be able to support very high level of security and scrutiny. The current way for us, and this is a bit dated, it's from 2008, this report, but this is sort of like the current way of dealing with tainted or suspect tainted devices, is actually to have some kind of a gold standard. You have a device, and the only way that you can actually tell if this device is real or not real is by having a real device that you can compare it to. And you probably realize that this creates a complexity for most asset owners because they don't necessarily have a reference article to compare it to. They don't know that this corner should have been looking like that corner in the plastic mold of the packaging. And that's sort of like the biggest concern is, how do we actually provide asset owners, those that are at the end of the supply chain, the ability to recognize whatever comes into their facility, whatever comes into their platform. Moreover, there's a concern about how to protect the security, the security measure. So how do you secure the security measure? If I have a security ink
or I have a hologram, or I have a watermark paper that, in this case, it's part of a solicitation for writing a request for controlled substances. In all those places, the list of things that you need to have is actually quite complex and quite difficult. If you are thinking of, let's say, having a seal, a serialized seal that you trust, if I want to ship it to you and it has to go through intermediates, how can we guarantee that what you're receiving is what I sent you? How can we make sure that the security measure hasn't been compromised before it was utilized? If we have concerns that our holograms are disappearing in the manufacturing floor when we're producing those boards overseas, how can we make sure that these measures actually survive the battlefield of actually being deployed in the supply chain? Moreover, and I know that today it's probably obvious that supply chains are fairly complex. They're not linear. They're dynamic. So this is sort of like a snapshot that is taken in time. This is related to the Joint Strike Fighter. There are about 15 hands. Every component is changing about 15 hands before it's being installed in a vehicle. 15 hands, 15 people are touching. There's 15 opportunities or 14 opportunities for somebody to try to insert something between two parties. And what's important to mention is that because it's dynamic, it's not necessarily something that you can apply a solution and sort of like let it run. You have to constantly change the dynamics. Can you hear me better now? Okay, good. Sorry about that. So being able to have a dynamic solution, some solution that will be able to be applied whenever it's necessary, but not always, because sometimes it's very challenging to actually apply a solution. Let's say I have a supply chain that extends beyond my secure perimeter to an overseas facility. Do I want to have a solution there? Is my solution will survive in that environment? And do I want to have it constantly in that environment? Or do I want to have to like handpick the specific items or specific opportunities for me to be able to tag? So if we simplify it into a supply chain, this is sort of like the use case for, here we're talking about a DoD customer, but you can imagine that it actually maps to other places. You have the component supplier, component manufacturers, the OCM, original component manufacturers, and then there's typically some kind of a supply chain and distribution channels. Then things are manufactured, boards are being assembled, and then they're integrated into systems of systems, and then they're passed on to the end user. And in all those places, there's a concern about what happens to those objects. Many of you in this room probably already know this, but the concern of counterfeits is tightly adjacent to the concern of tainted devices. If there's a huge gray market that will allow me to buy components that are equivalent in their performance and be able to populate boards using those equivalent or semi-genuine components, I can shave off a few cents on every component, and I can make, as a contract manufacturer, I can make more money. However, because I'm entertaining this possibility of introducing the gray market into the operation of my facility, I'm also introducing the concept of having other actors using those vectors in order to penetrate my supply chain or my the organization that I'm supplying those things for. So actually the ability to prevent counterfeits is closely tied to the ability to actually enhance the security from a tainted or a compromised solution. And what we wanted to be able to do is actually tackle both things at the same time under the assumption that at the end of the day, you need to be able to trust devices, you need to trust components. Once you can assume some level of risk, you can associate whether this is a non-genuine part that you can still trust. And these things happen actually in many cases. And this is, again, my apology if this sounds like too much like a sales pitch, but what we see is that this challenge of being able to trust objects, of course, there's a security concern in multiple sectors, from the automotive, automation, infrastructure, of course, defense and aerospace. But that security concern or the inability to associate data with objects, that trusted physical digital binding, actually manifests itself also in concerns about quality and value.
And sometimes it's actually easier to talk about value than talk about security, because if you're engaged with a customer organization about security, they typically don't want you to talk about that. So let's say that you have art pieces. In order for me to sell an art piece to Omar, yeah, good one. I need to be able to demonstrate to you that this is a genuine piece of art. If I cannot demonstrate that, if I cannot bring in an expert that will tell you that this is a genuine piece of art, or this is what it is, what I say it is, then it's going to be very difficult for me to associate value with the same piece of art. So there are two Jackson Pollock examples. There's one that had the very clear provenance and was sold for over 100, I think it was $160 million. And then there was a Jackson Pollock that was found in a garage where the provenance was not obvious, and it was only sold for about, I think, $20,000 or so. And that difference has to do with just not being able to authenticate where the art was or how that article propagated in time and space. The subject of quality or reliability is actually something that we were a bit surprised as a company that just emerged from stealth in November, how much interest there is in being able to actually maintain the quality. So I didn't know this until very recently, but if you look at the pharma space, there are over 1 million counterfeit drugs. There are 1 million people that die from counterfeit drugs a year. 33%, so a third of all the malaria drugs in Africa are counterfeited. This is a huge, huge problem, and has nothing to do with security. It has to do with the quality, has to do with safety of patients. In the same way, in the automotive industry, you have concerns about having genuine parts, right? In the luxury space, nobody died from a fake luxury bag, but a fake airbag has a completely different implications. So being able to authenticate things, being able to protect consumers and companies from non-genuine or counterfeit products is actually quite important. However, there is a problem in the ways that the solutions are laid out. Most of the solutions that you see out here, so here what we try to map is how well the solution can scale. So this is better, this is worse, and how good is the security? So you can have, there are certain classified solutions that are extraordinarily good, but they're quite limited in their ability to actually work with the market. Embedded IDs are excellent, they can scale, but they actually have the challenge of they can only fit on hardware that can support embedded IDs. So UDIs is not something that you can have a sticker with a UDI on. However, paper and barcodes and holograms are something that we can easily use, you can easily scale, but the security is not as good. And typically, what we saw is that there's a pretty good correlation between the level of security that you can get and the cost per item that you're going to pay. At the end of the day, the business model of most of those, most of the solutions that are offered in this in today's environment is actually tying in the level of security with the cost. So SICPA makes security ink for almost all the currency in the world. They also sell you stickers, ink on them. The stronger the security, the harder it is for somebody to reverse engineer the specific security ink, the more expensive it is going to be per tag or per sticker that you buy. And then there's a whole complexity of how you're going to actually deliver that to the customer. You cannot send it on FedEx. That's the issue. So what we decided to do is actually create this trusted physical binding. And again, our assumption was we cannot be the oracle that will tell you that this or that device is trusted or not. We cannot make that assumption that there's going to be some entity that will be able to cast this, let's call it magic dust, and once you put the magic dust, everything becomes trusted. No, that's not the case. But if you can extract the identity, if you can create a unique unclonable identity that can be applied to any object that you think of, you can actually allow for different stakeholders to add data to associate with those objects, and therefore
there is a way for other actors to be able to make an assumption about the level of trust that they can have with those things, where we sort of like stay out of the decision whether something is trusted or not. We're just providing the means to have this trusted binding between the physical and the digital domain. For that, at least in our view, the solution has to follow, there's 3 pillars that we call them. It has to be unique, so batch level identity, being able to say that everybody comes from the same town, is not a good way to do airport security, right? It's not sufficient to say that you're part of a batch. We need to be able to have a finer granularity, and sometimes that granularity has to be below the article level, so it has to be a component that goes in that, those boards, as an example. It has to be secure, and here, security is not binary, right? It doesn't have, there are things that are more secure, and there are things that are very secure. And we needed to be able to develop some solution that allows us to actually have a way to calibrate the security based on other conditions that may exist in the supply chain. For example, how much time we could spend on an object in order to accumulate those security bits as you move in a high throughput environment, or where in places where you're not necessarily need to be able to consume all those security bits. And the final element has to do with agile. It would be great to develop something, or it won't be that great to develop something that is ultra secure, that creates everything that we want, but is impossible to get out of the lab, impossible to get out in the field, and allow for those stakeholders at the end of the supply chain to authenticate things as easy as possible. And it has to be agile, it has to be something that's flexible. And what we decided to do is actually use those diamonds, and you haven't seen it here because it's hard, it's small. These are nano diamonds, typically around 200 nanometers and above. We do make nano diamonds that are significantly smaller, down to 10 nanometers. But in this application, we're using crystals, so some single crystal diamonds. This is a 3-dimensional rendering. But you have a crystal here, and inside the crystal, we engineer an atomic defect called nitrogen vacancy center. And that atomic defect, you can think of it as a 3-dimensional compass. It allows us to tell north, where north is where the magnetic field is. And what we do is that we, in our scanning device, actually allow for the magnetic field to change, and therefore we can actually do some kind of a projection measurement. You can think of it as shining a flashlight on those diamonds and then see the shadow. And based on some algorithm that we developed, we can cast this shadow several times and then be able to extract what the orientation of every one of those diamonds is. And this is represented here by those vectors. And this pattern that is not just the position of those diamonds, you can see them here. It's not just the position of those diamonds, it's actually the orientation of diamond that makes the solution so secure. So the reason that we call it diamond unclonable security tag is because those diamonds that are encapsulated inside a polymer matrix, if somebody tries to position those diamonds or to try to manipulate any of those diamonds, other diamonds will move in our system. And therefore, that coupling through the polymer matrix actually enable us to create a highly destructive yet stable identity for physical objects. Does that make sense? Yeah, you have a question.
I think I get it, but does every single one on the lower left-hand picture have to be there and be in the right position?
So we actually allow for Mother Nature to define the identity. And that's sort of like the thing. We have no way of positioning the diamonds in a specific orientation. When you're applying diamond either by spray coat or by brushing, you're actually applying a polymer with those diamond dust, and they're completely random in their distribution and orientation. Because we cannot do it, and we don't think that anybody else can, that's why the security is so hard.
Once you've laid it down, then you see what it is, and then that becomes...
Correct, yeah. So we apply the diamonds, and after we apply the diamond, we extract a fingerprint in the same way of arresting someone, or going through the process of picking up the identity. We're enrolling that identity in our system, and from that point on, we can use it. So
that orientation information allows us to support things like PUF, physically unclonable function, the ability to authenticate objects over open channels, because effectively what we can do is we can create a challenge response pair where the authenticator can say to the scanner, put a specific condition around this specific marking, and then ask what is the result that you're going to get. And because of the complexity of the system and because of the tying in of individual diamonds through the polymer matrix, there's no way for somebody to be able to fake those signals or fake the signature that we're getting from those markings.
So it's like a better birth certificate.
That's exactly how some people say, is that there's that notion of a passport for devices. You consume the UDI over, throughout the time, and this is sort of like the birth certificate for the devices, where individual components will have those credentials. Yeah, so thanks for mentioning that. So here, what we do, and again, it's quite trivial, and that's maybe the nice thing about it is every one of those components can have a unique identity. That unique identity is something that we have no control of casting. We just can observe it. And once that unique identity exists, we can tie information to. And this is something where we just became an SAP partner, and just to be able to demonstrate, we can reflect the information that we're observing on blockchains. So the ability to interface with blockchain, the trusted network that a lot of people are advertising for supply chain security. The question is how to interface with the physical objects, and this is sort of like where we come in. So we design our solution to really be identity management for physical objects, where that interface is what we want to take care of, and then be able to pull data based on the permissions of the user, based on the context of why things are being verified at different places in the supply chain.
So just for the bootstrapping problem, because now you have, I would guess, that the scanner, like authenticating the scanner, that's going to read the diamond matrix. About that.
Yeah, so you're saying, listen, you solved the problem with the objects, but you shifted the things. What's that?
It's very cool, by the way.
Oh, thank you. But you're saying, listen, you have a problem with the hardware, and you're going to have.
I'm just wondering. Wondering is now the scanner seems like that.
No.
Vulnerability.
Absolutely.
Yeah.
There's always a concern with hardware, with the credit card processing, POS systems that are, if you remember the Target concern that actually started a lot of the new cybersecurity efforts in the last 5 or 6 years ago, started with the point of sale, right? There was an attack on the point of sale. So being able to protect the hardware is highly important. And we're very happy when we get those questions, because that tells us that we solved the biggest problem, which is the things that are moving in the supply chain. I don't mind having concern about my infrastructure, my cloud infrastructure. I'm not saying that it's not something that we're very, very much aware of, and we're constantly building better and better security, and we're actually using other resources to secure both our hardware and our software. But the biggest concern that we wanted to be able to solve is how those objects that are moving in the supply chain, that are completely disconnected from any kind of network, you have still the ability to say, this measure is surviving, this measure is secure, even after exposure to, let's say, a nation-state actor that is trying to manipulate the system. So being able to shift the vector from the objects that are moving in the supply chain to an infrastructure that's supposed to validate, that shift, for us at least, it's a valid shift, because protecting the hardware is significantly easier than protecting things in transit.
Thank you. I still feel like there's an issue. Maybe I'm not understanding. But the diamond pattern has to be read by a device.
Correct.
That's set up to read diamond patterns.
Yes.
So that the security of that, the authenticity of that device is hugely important.
Of course.
Okay, so I'm asking about that.
No, it's definitely critical that, and the reason that I'm not saying that our hardware is ultra secure, because there's no hardware that we can let go of their chain of custody. So if our scanner ends up somewhere on the other side of the ocean, and there is an actor that can deploy whatever resources they want to reverse engineer a scanner, then there is a scanner that is going to be compromised. However, whenever they're going to use that scanner, we're going to get the credentials of who used what and where.
They never there it is. Everybody can see the scanner like scanner.
So, yeah, all right. I know exactly, that's what I said. I said there's a bootstrapping problem about how you have authenticity on your scanners.
The problem is, let's say someone manipulates a scanner so that it, so that it can be, so that it can be coerced into falsely reporting the signatures of the objects it's scanned.
But it cannot.
Yes.
That's
There would have to be a shop that had authority to send scans in.
So you need to have the credentials,
Yeah.
and you need to have the ability to have the secure handshake between our cloud service or on-prem service and the scanning device. And that scanning device has to have an object that is a trusted object to be able to penetrate.
So at a certain level, it's down to some level. The production shop has to have some controls themselves. I mean,
Yes.
there's a point at which you say you've got to have some. We're going to trust you up to a point to send the right.
Up to a certain degree.
information in.
But at the end of the day, what I want as an asset owner is to be able to make sure that every time there is a transaction, there's somebody that stands behind that
It's a
transaction.
shared responsibility.
Exactly.
They share some of those responsibilities.
Exactly. If I can point to the contract manufacturer, that the contract manufacturer scanned objects, and those objects, they happen to be false objects, I can still point to that entity, that stakeholder in my value chain.
Yeah, sure. Oh, and when they, at the point that they say, oh, look, we figured out that, XX through YY were, bad badge that were run under false pretenses, you can then go, find them in your database, right?
Exactly. And we can alert all the operators that there's a stakeholder that went rogue.
So
Exactly.
it's another kind of.
Yes, exactly. So how does it actually work? This is not as, yes, sir.
So you apply the code, that's the code for me. Put out an object, that's like rubbing off or CMP agreement or something like that.
Yeah, so the ability to destroy an identity, the dust identity exists. We want that to happen. We want to make sure that when you're decommissioning a device, you have a way to destroy the dust ID. And also, we're using the technology to be able to detect tampering. So if you put dust on a screw and somebody turns to turn the screw, we can alert the operator that a dust ID has been compromised, and therefore the device has been opened.
Sorry, if you don't mind me jumping in.
Sure.
This is a question. Is there any flexibility or wiggle room in the, I guess, environmental effects like degradation, being rubbed on because we look around transit, that sort of thing?
Absolutely. So durability, the question about durability is highly critical. We don't make the assumption that there's one solution that works on everything. The nice thing is that we typically allow for the customer organization to define what the polymer is. So if you have a medical device, being able to go with a polymer that is already approved for that medical device, for that application, which means that we need to just flavor that with a little bit of dust and then be able to go through a 510K process instead of a full FDA approval. If you have in the aerospace, you have polymers, or in the electronic industry, you need to be able to have a mil-spec optical epoxy that can survive 360 degrees Celsius or something in that range. And we have polymers that can operate in those environments. There is the fingerprint method is the same. Dust is the same diamond dust in all of those cases. It's just that the host material can be varied and can be configured for this specific application requirements. For the pharmaceutical industry, and I know that you're one of those, cold chain, maintaining the cold chain supply chain, so the raw materials, there's a window of, I think, 4 degrees Celsius that you have to have the material coming in. So being able to create a polymer that will have some kind of a deformation at those extremities is something that is a polymer science problem, and it's not a security problem. By being able to incorporate the two, we actually can create a solution that can alert the operator when something goes out of that thermal schedule, and be able to make sure that all the stakeholders in that environment can do it. And the nice thing is that it's extremely, extremely inexpensive. So don't associate diamonds with being an expensive solution. The cost of putting diamonds on things is many fractions of a cent. And that's sort of like the beauty of it, is that you don't need to really have a really expensive solution on the objects in order to have an effective and secure solution. So what we do is that we take diamonds, and this is a relatively small diamond, so I think it's 35 nanometer diameter, and you can see that the diamonds that we're using have some random shape to them. They're not all beautiful. Most of them are, but not all of them. And within that very weird shape of a rock, there are several things that we need to take into account. The diamonds are carbon. This is a carbon lattice. There is a nitrogen. Typically, nitrogen is an impurity that exists in most synthetic diamonds to some degree. There's sometimes 200 parts per million of nitrogen in a regular diamond crystal, sometimes 10 parts per million. And what we do is that we knock out one of those carbon atoms next to a nitrogen center. So we take the nitrogen and we take the carbon and we knock it out. That's a vacancy. And it's the nitrogen vacancy vector that actually is the element that we're looking at. That's the compass that we're looking at. So it's a defect center that is 2 atoms in size. The only thing that I didn't mention is that we don't look at one, we look at 300,000 we're raking, and all of them are crystallographically aligned, so all of them are sitting on the same crystal, and therefore it gives us that high fidelity signal that we're looking for. The final thing, and this is sort of like, if you haven't figured it out by now, my PhD is in materials. I'm not a cybersecurity expert. But it's the surfaces. So when you're thinking of a nanomaterial, when you're thinking of nanotechnologies, it's really a process about surfaces. Nanomaterials have a huge surface-to-volume ratio. And it's actually working on those surfaces, working on that interface that allows us to be very stable in different polymers, being able to calibrate the durability based on the application. It has to do with a lot of the effort that we spend on actually creating that interface layer, that diamond polymer interface. You had a question?
So does the fingerprint come from like a single diamond in the group, or does it kind of calculate the whole layer of diamonds? Like if the scan looks at that picture, can it like tell you the idea of each diamond, or does it kind of look at, there's these diamonds together in this pattern, that's the fingerprint of this object?
So every one of those diamonds will give us a different signal.
Okay.
This is a spectrum in RF. So this is microwave, around 2.87 gigahertz. We're not picking up this signal in RF. We're picking it optically. Okay. But every one of those diamonds will have a splitting, so zero-thread splitting. Degeneracy has to do with the extent of the strength of the magnetic field, or the difference between the dot product between the magnetic field and the crystallographic orientation of the diamond.
So it looks at how the diamond is pointed in.
Yeah. So this is our magnetic field B, and this diamond is pointing this way. So we're looking at what is the projection of this signal on this vector. And then we're doing it simultaneously on all the diamonds in one shot.
If someone came through there and like knocked off like all the diamonds from a product except for one, like let's say you're trying to trace down like someone stole an electronic shipment, like one diamond was left on there.
No.
You couldn't. So you need multiple diamonds.
We need multiple diamonds to have a signature that we can trust. Being able to manipulate one diamond, we've done that at MIT. These are things that it's hard, but it is possible.
Right.
Being able to manipulate more than 3 diamonds is an impossible problem. And that's sort of like the challenges is that, and we're looking at 400 as a minimum fingerprint, and we have thousands or hundreds of thousands of diamonds that are being sprayed on the object. In terms of serialization space, and I expected that to come from this crowd about how big is our serialization space. The level or the number of bits that we can accumulate on the angle resolution, we have about up to 12 bits of resolution of angle. But let's say that we only had 3. And we only had 10 diamonds. And we only had a chessboard. So we can put the diamonds, those 10 diamonds on a chessboard, so 8 by 8. And we only have about 3 bits. So a quick question, how many combinations do we have? Well, it's a lot. It's crazy amount. So I don't remember the exact number because typically we say it on a 10 by 10 grid, but I think it's something on the order of 200, 10 to the power of 230 or something of that order. So it's not just how the entire group of diamonds is oriented, it's like where they are in their orientation. So
Yes,
okay.
yes. So it's the position. So think of it as a constellation of stars.
Gotcha.
And then every star will have a specific orientation, and then you can scrutinize that orientation to certain degrees or certain number of bits.
Gotcha.
And that will give you also the ability to accumulate security, also expand your serialization space whenever it's necessary.
Cool.
Quick question: how does that compare to modern cryptographic photography? Do you have any quick stats on that?
So we have, I think that we need about 5 diamonds to be at the same level, or 5 or 7 diamonds.
This is way better.
It is way better, but keep in mind that you do need a dedicated hardware. So this is not something that we can just spray on a motherboard, and now we have a motherboard that we can authenticate over the network. Not yet.
I get the difference.
We're working on it.
It's still cool.
Do you have any diamonds on your hands?
On my hand?
Yeah, it doesn't seem to wash
If I have diamonds on my hand, probably at one point I had diamonds on my hand, but diamonds are safe. So, and we're using 200 nanometer above for the cytotoxicity concern of that material.
Yeah, I realize you use the identify I guess it relies on position. It just would be interesting to identify some tampering based on the specific diamonds they have.
Oh, yeah. So there are solutions. We use it in explosives, trace materials. So you can detect explosives based on certain molecules that are detectable at very small concentrations. I should maybe want to point out here, there's no specific signature. We don't rely on this. Our security is not reliant on the fact that somebody cannot make diamonds the way that we're making them. We have to operate in an environment where there's a nation state that want to reverse engineer, and we just have to make the assumption that everything that we came up with is already exposed. And the question is, under that assumption, can you still provide security? And our answer to that is yes, because we're using a random process to create those identities. So we won't be able to give you a trace because our identity is based on the fact that those diamonds are encapsulated in a polymer, and that is a cohesive identity. We have scanners that are able to burn a hole. So let's say that somebody tried to authenticate an object outside of the perimeter where that object should have been. We have a way to actually destroy that identity on the fly.
We shouldn't tamper with something that's not polarized.
That won't change a thing, no.
What if it won't?
So we're focusing on the tamper detection on the device itself. So on that circuit board, let's say that we put the dust on the testing pads or programming ports. If somebody tried to access them, somebody tried to insert a needle through the dust membrane. So think of it as really a thin membrane of plastic that encapsulates, that has diamonds encapsulated in it. If somebody tries to penetrate that membrane, we can alert the user that somebody tried to move the cheese or move the diamonds.
So, if I understand this, you take your diamonds, you sprinkle them into some polymer, you paint them onto the soles of your shoes, and now you've got diamonds on the soles of your shoes, and you've got to now record that.
Yes.
So do you have to build consensus, or does one guy recording it control your whole network.
So what we did is that we designed a solution such that the authentication authority, so whatever is where the data is, and the place where things are being identified, they're separate by design. They can exist on the same hardware, but they're separate by design. And when I am applying dust on something, and then I'm enrolling it in the system, that enrollment will go into Authenticator, or the authentication authority, that will be used to be able to verify the hardware or verify the ID later on. So yes, the entity that is doing the enrollment is the gatekeeper in the supply chain. These are entities that you say, I trust you well enough to enroll those dust IDs.
So are you using like a distributed ledger so that you've got some level of consensus of, so what if you get a bad actor who's an enroller?
We don't make the assumption about who's authorized to do the enrollment. We allow the customer organization to define those gatekeepers. That gatekeeper doesn't necessarily need to be 100% trusted. They just need to know that from this point on, you can verify everything that they've done. And from that point on, they tend to align with the interest of the rest of the supply chain. And that's sort of like what we want to be able to do, is actually drive accountability and trust in the supply chain. I have a 10-year-old, he's great. He's incredibly smart, very creative. But I would bet you that his ability to do his homework is going to degrade over time if he'll know that nobody's checking his homework. And that's effectively what we have in supply chains, is you have this contract manufacturer, you have the distributors in your supply chain. You sort of like make the assumption that they do what they're supposed to because you have some kind of contract with them, where your ability to actually verify what they've done is actually quite difficult. We wanted to make sure that I can communicate to my suppliers, I can communicate to my supply chain, my distribution channels, and my service operation in all those places, that now we have a way to verify what is being done and what is being installed and what is being verified. And that sort of like is the key, is actually to drive a change in the behavior of the suppliers such that you can improve the security.
You're going to know that it was a guy named Joe who painted my shoes, and he registered them. And if they turn out to be a bad pair of shoes,
you can go back to Joe and say, I think that we have a problem in our relationship. Yeah. And keep in mind that most of the concerns that we see in supply chains is driven by the fact that different actors will claim, oh, your shoe never came through our part of the supply chain. You brought the shoe by yourself, your IT department bought it on eBay. Well, that shoe is, yeah, maybe on eBay.
But once you've been recorded in the ledger, you can't.
Once you have this chain of custody of who touched the object, whether it's a distributed ledger or centralized or semi-centralized, whether you have one authentication authority or multiple authentication authority. So I want to make the distinction between a distributed ledger, so being able to maintain the integrity of data, to how many stakeholders are allowed to authenticate something. Let's say that you are a defense contractor or you're a DoD customer, and you bought a Samsung device. You may not want Samsung to be able to authenticate, to be the authentication authority for you when you're consuming the device. And there is a way for us to actually move the authentication authority from the public supply chain to the secure perimeter to the classified environment whenever it's necessary. And just to summarize, and again, deeply apologize if it sounds like a sales pitch, but what we're doing is actually providing this end-to-end, cradle-to-grave authentication capabilities of objects that can be extremely small and can have tamper detection capabilities and can go on a wide range of applications. I want to just make the point, and I know that this is a security forum, but it's highly critical that we understand that there's a lot of good folks out there that are deeply concerned about quality. And I think that a lot of times I see that the folks from the security think of the quality well, it's not a security problem. We don't care. Nobody can hack us through the batteries, and because of that, we don't give them as much of a support as we can. And I think that understanding that a quality problem and a security problem are actually quite tied together in supply chains will help us actually bring those very different disciplines to actually support and help improve the reliability and integrity and availability of those critical systems that we all rely on, whether it's the grid that we had somebody here from. I've spent a lot of time developing cybersecurity tools for the grid, or a defense platform, or data center. In all those places, we need to have just better security. And with that, I thank you. Yes, ma'am.
Years ago, I had a client in the USA who had a problem with, that was his big thing in procurement, right? We pretty much, it looks like a Cisco router.
Yep.
Acts like a Cisco router, right? So I'm wondering, like, do you see that this is something that multiple governments can use? Like, I guess if multiple governments used it and multiple state actors use it, does that make them all more secure or all less secure because they're all in the same?
Yeah, it's a good question, because that ability to operate with multiple stakeholders that don't necessarily have the same incentives, or they're not sharing the same common goals, is something that all supply chains typically have, right? The very easy way to define a supply chain is that you pick a space, you pick a specific entity, and then it's fanning out in both sides, both the upstream and the downstream operation. I want to point out that what we're doing here is that we're creating biometrics without the bio. So we're really creating an identity. That identity doesn't carry information. It's the ability to ask, using those identity credentials, to request information from stakeholders that you have some prior agreement with. So if you have different countries or different entities that maybe are competitors, they don't need to share information in order for them to benefit from the same tools, because we separated that identity layer from the data. And because of that, there's that independence where we can have everybody in the room to be part of the same network, and then we have an agreement to pull data only from a subset and provide it to you, because that's sort of like the relationship that you have with those specific suppliers. If that makes sense.
More questions?
Security isn't a zero-sum game.
Well, is it? It's not.
In other words, to that question, you can have multiple, you can have people who in theory are adversaries in terms of China versus the United States.
I think that because its security is not binary, and the ability to trust is something that you need to gain this granularity, it's actually being able to build that economy of trust, and I think is quite interesting. So to your point, yeah, it's not a zero-sum game. There are ways for everybody to benefit, where you don't have to eat away from somebody else. If that's your point. Yeah.
And is this diamond dust easy to come by?
So I didn't tell anything about that, but it took us 2.5 years to develop the diamonds that we're using. So we're actually not making diamonds straight from scratch or from carbon. We buy diamonds that are coming from the abrasive industry. So there's synthetic diamonds that are being produced in metric tons a year. So a lot of diamonds that are on drill bits and razor and scalps and other things. We're buying the diamonds that are simply too small to be used as a good abrasive. So we buy the waste from the abrasive industry, and then we develop a process that is actually took us a little while to figure out, but we developed a scalable process that allows us to make the diamonds at scale, where the cost is incredibly low, such that we can. The biggest problem for all the security solutions that we've seen out there is that it's just cost prohibitive to deploy in production. And we wanted to say, put dust on everything, and then let's configure the security based on how you're scanning at different stages in the supply chain to a subset of the devices that you have dust on. And that's sort of like the ability to decouple our pricing, our strategy, our revenue model from the bill of material is actually, I think, something that is quite interesting for the device makers.
So your goal is just everything should have dust on it. If it never gets scanned because no one cared, okay.
I think that that can be an effective solution in many cases where and again, we're a small company. We just came out of stealth in November, and we cannot make the assumption that there's going to be some kind of somebody that will be able to say, okay, now everybody is dust enabled. So we need to be able to be dynamic and operate in places where you cannot go to the manufacturing on the first day. You cannot influence the design at all. You should have minimal friction on the bill of material and still be able to be an effective measure for the most the customers of your organizations that require the most security at this specific time, and that population will keep on changing because their device requirements will be different.
So, in terms of that, is trying to ask that question, the follow-up question would be the scanner. So,
yeah.
Dust itself, you consider it to be prohibitively inexpensive, but what about the scanners?
So this is a good question. So the scanner cost is based on certain factors, including the level of security. So how many bits we're supposed to accumulate, how hard the security is around the scanner itself, and how fast it's supposed to operate. So if you're thinking about high throughput environment where you have 10 milliseconds to scan every object, that's a very different environment than a field scanner that can look like that and doesn't necessarily need to have all the security at the beginning of the line.
Sorry, I should have differentiated that. Glad I didn't, but yeah, so there's also the scanner when I want to verify.
Yes, it's the same scanner. Yeah, and you had a question.
I'm just wondering about the process of applying the dust and its matrix to different materials and what you found.
Yeah, so this is our field operator kit. This is how you can apply dust. So
nail polish or something?
It looks like nail polish. It's significantly easier to fly with something that looks like nail polish. And actually, it's quite close, so I don't feel like I'm violating the laws here. This is acrylic bottle. Nail polish is acrylic, for everybody who didn't know this till now. It has slightly different elastomers, so the other molecules that are inserted are a bit different than a commercial nail polish. And then there's diamond dust that is saturated. So you're welcome to see there's diamonds that are settling here. So the cards, these cards, I feel like I'm mentioning all my family, but my 5-year-old daughter actually painted all those cards for me.
It sounds like, so that's a manual process for high value objects, but I'm just wondering about
spray coat.
You're really talking about the scaling, and scaling of this. I'm just wondering about that and what it works for, what it doesn't work for.
Yeah, so we're compatible with print inkjet nozzles, certain type and certain polymer. Spray coat is a very common way, so conformal coating for electronics. Any circuit board that goes into flying objects typically go through a conformal coating process, and we can flavor that conformal coating with the dust, so we can apply it that way. There's
so that
certain
would just be adding your product to whatever is already being sprayed on.
Yeah, so there's typically a master batch, and during the master batch making process, we can dust that master batch to be dusted. Yes.
So if I understand this thing correctly, basically the identity is tied to a patch on the surface of the object being authenticated,
yes,
which is covered, which is at the diamond, invested, painted on.
yes.
So if I was a nation-state adversary trying to inject counterfeit Cisco devices into somebody's supply chain, what prevents me from buying a bunch of genuine Cisco devices, extracting the portion of the surface which contains the authenticity tags, incorporating those into the surface of my counterfeits in some way that's itself, difficult to detect, and I can do that because, I'm a nation-state adversary who knows how to weld plastic, and shipping them off.
Absolutely. So The primary driver here is that it's impossible to copy, so to lift off that dust ID and put it on something else. That's impossible. If you're cutting off, so if you have a broom and you put dust on one side and you chop it in half and then you added a different end to it, yes, then there is a way for somebody to falsely authenticate. That's why.
What I was thinking, what I was thinking of was, I mean, let's say the tag is on a plastic case.
Yeah.
You can cut out the bit of plastic.
Yeah, so that doesn't seem to work. That ability to transfer parts of objects doesn't seem to work, where it typically falls the scrutiny of the operator. So if the operator looks in something that looks obviously like something was glued on.
Right.
Yeah.
Well, yeah, and I mean, so here's where Vicino, you basically postulated the science fictional capability of independently transferring a patch of plastic.
Yeah, and that's sort of like the challenge. And keep in mind that the minimal footprint that we require is 100 microns by 100 microns, or the cross section of a human hair. So you have to be really delicate when you're moving those things around. Yes, sir.
So I know I asked you this when we first met, but the use case that obviously got a lot of attention was the Supermicro motherboard, where again, according to Bloomberg, there was a tiny particle of sand-sized component that was allegedly the malicious component.
Yep.
We actually don't know what the component was. That was the implication on a very large server motherboard with thousands of different integrated circuits and other components on. So kind of bring us, so using that component, that Supermicro motherboard, Supermicro is a customer of Dust Identity, or if they were, how would you be securing that? Would it be a film over that finished motherboard at the factory? Would it be films on each of those individual components where they were fabricated and then sent to Supermicro, or how would it work?
So I think that first of all, there are multiple ways to address that, and it really depends on what the customer organization. It's typically not the device maker. I should just point out that typically we really want to work with the asset owners that are in charge of the platforms.
So not Supermicro.
Supermicro is a vendor to those operators, to those stakeholders. Okay. We wanted to give, in that context, the ability to be able to make sure that individual components that show up on those boards were sourced correctly.
Yes.
So if you bought your components, typically you buy them from DigiKey, we can work with an entity like that and allow them to dust individual components, and then we can verify that those components actually were showing up on those boards, and nothing but that. If there is an interest in just improving the resiliency or helping the contract manufacturer to better communicate their value, better communicate their accountability behind what they've done, they can seal the board after manufacturing and basically apply a code and say, I stand behind this product, and this product came from my facility. And if you will claim that somebody inserted a component, I can demonstrate to you that this has not been done in my facility because I created a seal over everything that I've done. So that's
you can have multiple layers.
Yes, absolutely.
The chip company could label his chip, could dust his chip.
Absolutely.
And then the board company could dust the whole board.
Yep.
And then the case company could dust the whole case.
That is true. That's the hierarchy. The physical is staying within, in our view, at least two layers. So component and assembly, but the external device is spray coated with another layer that is just associated with the components inside. Yes. 1 second. Yeah.
So is there a waterfall impact on security in the sense of, so if I'm a bad actor, now I know, like, you have a database of things that I know to be true and 100%, and now, like, there are like privacy implications of that, because like before, like you're saying, like supply chains, like, there's some pallet, who knows what's in the pallet, and now it's like, now I know exactly what's in the pallet, I know that they're all valid, I know all these other things. So Like, is there something that because I'm using this, I now have to change other aspects of my security program?
Definitely, whenever there's information, when there's customer information, we have to be very, very conscious about that. I maybe want to point out that we're typically, don't make the assumption that we're the custodian of the data in those cases.
I wasn't assuming that. But
So I can have a collections of ID. I can have a collections of ID. I don't necessarily need to know what they are, what they're referring to. I just know that there's a collection of IDs that have some associations, and I can only give you that information if you have the right credentials. So the permission-based viewing, permission-based writing into our platform is something that is, it's highly valuable because we don't make the assumption that transparency is really about being able to have all the data available all the time to all the stakeholders. If that makes sense. Yeah, question.
Yeah, so like what if you did something with different layers, like can you scan through like different layers of polymer?
To a certain degree. So we can penetrate several millimeters into a transparent piece of plastic. If the plastic becomes opaque or tainted, then we need to be able to be closer to the surface. If you have multiple IDs that are stacked together, I don't think we tried more than a few because it was never a requirement. But it's really about focal depth. So think of our optical system as a microscope. You can focus to different levels. It's called the Z-stack microscope.
For your camera, like if I, so like let's say like I'm a server manufacturer, I manufacture this giant server. It's got giant motherboard. It's got thousands of components.
We should talk. Yeah.
Has a dust stop, has like dust on each component.
Mm-hmm.
And I take the camera, and I take a picture, and I want to scan each component to verify that it's the original component I modified.
Yeah. So our typical standoff is around 7 millimeters, and it's really designed to couple with the visual inspection systems, the automated visual inspection system that you have in your manufacturing as a board maker. So it's about being able to get a layout, board layout, and then be able to define which components need to be verified, and then go hop between them.
Okay, and so you kind of take a picture of each component individually, check its fair, but you could do like a single picture of the whole board. And then
so
check everything.
From right now, no. Have like a flatbed where you put the, but then there is an issue of, I know that it looks like the board is flat, but it's not flat. There's topology, and then being able to just capture all the identities of the right fidelities.
There's also an issue of like there's an integrated circuit on that board, and someone goes in and just like sneaks in the side of it for some sort of real small technology, gets in and changes something inside of it. So it's just that one portion of dust that's been disturbed, and detecting that one like couple millimeter wide, chunk of dust has been disturbed on the entire server, server board.
Again, I'm not trying to sneak away from the question because it's a very important question. We allow for the customer organization to define how they need to protect their boards.
Okay.
We can suggest several things, and typically the way that we're approaching it is that you have a board, and then we're going to define certain vulnerabilities. We're going to say, okay, this is the number of touch points that you need to have, but ultimately it's the responsibility of the customer organization or their agents to be able to define what needs to be protected on that board. Because we cannot assume that we understand every board that is being made.
I'm more wondering about like performance speed. Like if I take a picture of my board, I need like every minimal set on that board check. Like how long the fastest scanner take to scan that board?
So we're hovering around 10, 12 milliseconds on a scan as a single scan, and then there is the mechanical translation. So it's fast, but it's not as fast as thinking of taking a single picture and having the entire thing laid out. But typically, those type of deep scans are done offline.
Right.
So you have a QC station or a security station next to your line, and then you can spend several seconds on authentication.
I know you just came out of stealth, but can you tell us a little bit about use cases right now or implementations?
Yeah, so we're primarily focused on government and defense currently. We have engagements with several entities in that space, also commercial entities that are
You can
we
tell
just
us which
started.
ones, right?
Unfortunately, they tend to be quite secretive about this.
Shocking.
I hope that we'll be able to talk about some of those engagements, because I think that it's actually beneficial for those customers to talk about having a solution that it's like advertising that you have a new alarm system. It's beneficial.
Except you don't want to say which one.
Which one? Sorry.
Which
what?
alarm system?
Well,
Which alarm?
I work for a security company. A lot of our customers typically don't want us to say that they're our customers. Right?
Yeah.
Because that gives them a bit of an advantage trying to figure out how to break our experiences.
Yeah, but this is not it's true, but maybe analogy is a bit broken here, because if your suppliers, so let's go through the logic here. If you're worried about a nation state actor not knowing, then I think we need to have a conversation about it. Because most likely the most sophisticated actors are well aware of what you're doing. So the question is, the fact that you're not talking about deploying a solution, is that helping or preventing you from extracting the most value? Because we believe that if your suppliers now have an understanding that you can check their work, the good actors are going to behave better. The bad actors are going to fear. And because of that, you create that discrepancy between the good and the bad actors. Yes, sir.
So when you scan, you get a bunch of raw data, presumably, and you create a signature out of that. Is the signature the raw data, or is it some?
So unfortunately, I ran out of battery on my laptop, but what we store is not images. So what we've done is that we extract the physical model of a dust ID. So we actually store something that is actually quite light from a data payload standpoint. It's only the description of the constellation of those stars, those diamonds, and their orientation. And then we use that physical model and we're shoving it back to the authenticator and say, is this model going to fit the specific model the specific ID that we're verifying against? So we don't compare images, we're comparing models. So if that makes sense.
Is it an exact match or is it an approximate match when you?
It's a biometric tool. So exact there's no exact when you go from physical to digital. There's always things that are getting smeared. There's always out of focus. There's always noise. So we spend a lot of time actually going through that structure.
Some equality or similarity factor.
Yes. So like any biometric tool, we need to exceed a certain threshold in order to say, you're the person that you claim.
But what you store for the signature is the exact data that you have from the scan.
It's not the exact data, but to a great degree, yes. And we allow for certain things we allow for certain normal changes to occur on that model such that we can search. Let's say that you plucked out some of the diamonds out. The physical model would be different. So categorically, I should say that they're not the same ID. However, we can tell you with high level of certainty that it's the same ID because we have enough redundancy in our system to claim that. If that makes sense.
Yeah, so you're saying, okay, this is the same thing, but it's been tampered with, or at that point?
It depends on, these are definitions from the customer organization. So if the customer say, any change, I need to be able to escalate the operator to say this is something suspect counterfeit, suspect tainted, and there's a whole process that goes after that because you have to go through quarantine, you have to alert certain entities. It's a claiming an attack when you don't have an attack is something that you actually don't want to have. So we typically allow for the customers to define what is that threshold, how much of wear and tear, normal wear and tear is acceptable, and what is a clear attack. And these are
that based on your own experience.
Pardon me?
Can you give them guidelines for that?
Absolutely, yeah. We have, for the electronic, so certain things we know a little bit better, but for example, in the electronic manufacturing, passing through certain processing steps. For example, there's something called degreasing, which is a very chemically aggressive process. Then there's a certain degradation that we can anticipate reflow of, and we have certain numbers. And we have the ability to select advise the customers whether it's a normal wear and tear or something that is a bit out of the ordinary. Yes, sir.
Is there any impact on temperature change between when it's first read and later verified?
Yes. So if you have a polymer, so when polymer melts, they don't melt. It's called glass transition temperature. So when the polymers reflow, our dust ID will deform. And that's something that will destroy the ID. So if you have a marking that goes on a system that goes through very high temperature and then comes back down, our ID will be destroyed.
But let's say just some optical depth variation. Not so much that it melts and slides off.
So for certain materials, not all materials, but we have mil-spec materials that can go through quite rapid cycling. The biggest concern when you have rapid cyclings or when you have a high extremes of temperature is actually the adhesion of the, so you get delamination. The thermal expansion coefficient of materials is different. So when you have two materials that are experiencing a very rapid temperature change, one will expand at a slightly different rate, and then you can have delamination. That's why you specify in advance what type of thermal schedule you need to go through. I want to mention that if you have delamination, our dust ID is no longer usable. That portion is no longer usable. Yes, sir.
You mentioned something about blockchain earlier. I'm wondering if that's an integral part of your system or if that's just something that's an idea for somebody to use.
So we're not a blockchain company, for good and for good. I think initially we thought that the whole mumbo jumbo about blockchain is we couldn't understand how maintaining the integrity of data helps in supply chains, where we were facing the fact that I can have mugs that look the same, and I can tell you that this one is on the blockchain, and then I can switch my hand, and you can't tell the difference. And we were trying to figure out, it was a year and a half ago or so, how do blockchain solutions try to interface with the physical world? And then we were told, oh, there are QR codes, and then there are NFC tags. And both of them are unusable from a security standpoint. One is too expensive. NFC tags are extremely expensive, and you're just not going to, even in the ultra luxury goods, NFC tags are too expensive. Okay, so that's what we found out. And QR codes are simply not secure. So the question is, how do you interface? And we were approached by several people that are coming from the blockchain space, and they said, can you help us anchor our blockchain to data, to the physical objects? And we said, why don't we just try? And then we started developing a relationship with SAP that was just building up their Hyperledger Fabric interface, and we became a partner for them on that product.
So it sounds like that you don't care.
We're agnostic to the blockchain environment. We can operate on blockchains because I think that I personally understand the value of blockchain. It's a way for me to demonstrate to you that my data infrastructure hasn't been compromised because the data now resides in other places. I can leave those breadcrumbs, those hashes across the network, and that's great. But again, it's not mandatory to have a blockchain. Actually, in the demo that I've shown, one of the things that we can do is actually chain objects on the fly. So we created something like a Amazon Buy Now, where you just click a button and things happen. So we created just the simple code of taking this object, taking the metadata, and then putting it on a blockchain that you have permissions to write into.
I don't think blockchains are very secure and they can fork. But you know, if somebody wants to use it, great.
So we're not storing any of the actual data for verification on blockchain. We're only storing breadcrumbs. We're only storing hashes. It's a way for us to reflect information such that you'll know that actors in the supply chain that may have data payloads, that data payload that you just received from one of the actors, we have a way to show you that that data payload matches the data payload that they used during the previous transaction, as an example.
it's not about storing data on the blockchain.
But still, I mean, a blockchain, I don't know, it depends on what you're verifying, but
yeah,
but you can make stuff up and
I agree that blockchains are not ultimate security, but they provide some means to trust the network. I think that's what we're all after.
use Merkle trees as well. Same way.
It's not a so distributed ledger is not fundamentally a new technology. That's like the challenge for a lot of the people that are coming from that space is that they feel this is we've seen this before, right? So that's a good thing. More questions?
Hand for Ophir. Thank you so much. Great.
Thank you.
All right, folks. Thank you so much for coming, and thank you to Ophir Gaathon not only for the presentation, but tonight as well. And stay tuned. We've got more stuff coming up in May. But we'll let you know. Thanks very much. If you haven't taken our member survey, please go online. The link is listed on the page.
Thank you for doing this.
No problem. Thank you. Thank you. I appreciate it.